तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Right, we are going to spend some more time now on the properties of spinning particles, specifically with regard to the spin of the electron, because this is an extremely valuable probe, not just in particle physics but also in condensed matter physics and many other areas of physics. So it is worthwhile spending some time on this and telling you how the spin of an electron behaves under applied electric and magnetic fields. If you recall, just to recapitulate, since we had a bit of a gap, the spin operator for an electron S has three components, S1, S2, S3 or Sx, Sy, Sz, which obey the angular momentum algebra, and they are represented by H cross over 2 sigma, where sigma are the Pauli matrices. Each Pauli matrix has eigenvalue plus or minus 1. So this guarantees that any component of the spin of an electron, the intrinsic angular momentum, has eigenvalues plus or minus half H cross. So the spin quantum number is a half for the electron. Okay, so this corresponds to S equal to half. As you know, if you have a quantum number J for the angular momentum, then the subspace in which the states of this angular momentum live is 2J plus 1 dimensional. There are 2J plus 1 values for the eigenvalues of any component of S or the angular momentum. So in this case it becomes 2 dimensional, and therefore the states that you could talk about are half, half and a half minus a half. This corresponds to the quantum number S, which is always a half for an electron, and this corresponds to M, which is M times H cross is the eigenvalue of any one component of the angular momentum, and we will conventionally take it to be the Z component. Okay. Then a very convenient representation for the spin operator is this thing here, and recall the definition of the Pauli matrices. We have written this down several times: 0 1 1 0, sigma 2 equal to 0 minus I 0, and sigma 3 is already diagonal, it is 1 0 0 minus 1. There are numerous properties of these sigma matrices which I have written out and which we have come across earlier when we studied linear vector spaces. The square of every sigma matrix is the unit matrix, 2 by 2 unit matrix, and the eigenvalue of any of the sigma matrices, the eigenvalues are plus or minus 1. They do not commute with each other. This one is already diagonal, so once you have diagonalized that, the other two cannot be diagonalized simultaneously, but any one of them could be diagonalized, any component could be diagonalized, and the eigenvalues would be 1 and minus 1. Okay. This state of the electron corresponds to the total quantum number, angular momentum quantum number half, which we already know, and Sz eigenvalue is plus half H cross, and this corresponds to minus half H cross. Since we have in the back of our mind what happens when you apply a magnetic field, in which case you have either this state or that state for the magnetic moment, it is conventional to call this in shorthand a spin up, if you like, and this is a spin down, if you like. The understanding being that the basis that you choose corresponds to states in which Sz is diagonalized, so eigenstates of Sz. Okay. Then the orthonormality relations are of course up up equal to 1 equal to down down, and the scalar product down with up is 0. Okay. So this is going to be a very convenient notation for us to use this notation. We are going to talk about several spins, then this will become very helpful. Okay. Now what is the actual representative of this guy here? Remember that this could also be written in the basis, natural basis. You could also write this as 1 0, and this could be written as 0 1. In any 2-dimensional linear vector space, you could choose 1 0 and 0 1 as the orthogonal independent vectors which form a basis in this space. Okay. Now why are we making such a big fuss about it? The answer is, even though the quantum number half is extremely small compared to classical quantum numbers, for instance we know that the angular momentum component, any component, has value plus or minus half h cross. That is actually true, and angular momentum is quantized for any angular momentum. So if you took, for instance, if you took a stone weighing 1 kilogram and you whirled it round in a circle of 1 meter radius, mr squared is 1 in standard international units, that is the moment of inertia, and if you chose the time period to be 1 second for example, then the angular frequency is 2 pi. Okay. Therefore the angular momentum is I omega, which is 2 pi joule second, which is enormous, but that 2 pi joule second must also be equal to some angular momentum, orbital angular momentum quantum number multiplied by h cross. This must be of order 1 or 2 pi, but this is of order 10 to the minus 34 in these units, and therefore this quantum number is 10 to the plus 34. That is so enormous that the discreteness of the angular momentum completely gets washed out, absolutely. Whether you add 10 or 100 or whether you add a million or a zillion, it still does not matter. 10 to the 34 is an enormous number. That is the reason why you do not see angular momentum quantization in daily life in macroscopic objects. But it is a very different story when you have a quantum number like a half, and this is indeed tiny. So this whole thing, this has eigenvalues plus or minus 1, so you can see numerically this is extremely small in the normal daily units that we are used to. Okay. So how do we find it? How do we detect this spin at all? The answer is that this spin also implies a magnetic moment for the electron, and that magnetic moment would couple to applied magnetic fields, and then you can manipulate the spin or probe the spin of the electron using the magnetic field or using various protocols for the magnetic field, switching them on and off in different directions, etc. And how is this done? A little bit of how this thing gets involved. Let me mention this. The magnetic moment of the electron mu e, as I pointed out last time, is equal to the g factor of the electron, Ge, multiplied by the charge of the electron divided by twice the mass of the electron times the spin operator, the intrinsic angular momentum operator for the electron. Okay. But this is equal to Ge, which is 2, and now I will explain why this is 2, where it comes from rather. This turns out to be 2 for the electron, multiplied by the charge of the electron, which is modulus E with a minus sign because the electron is a negative charge. Let us keep track of all the factors here, divided by twice mass of the electron, and the spin of the electron is h cross over 2 times sigma. The reason it is convenient to do this is because this sigma is dimensionless and has eigenvalues plus or minus 1 for every component. Okay. So that is a factor that goes out, and then no other numerical factors. Okay. And one of the 2's cancels, and you end up with this is equal to minus mod E h cross over twice me sigma. And of course you are familiar with this object. That thing is the Bohr magneton. Okay. So you could write this as equal to minus mu Bohr times sigma, and this guy here is the Bohr. It is the natural unit of magnetic moment which you get for a particle of charge E and mass m sub e. When you put this thing in a magnetic field, then there is a extra contribution to the energy of the system or the Hamiltonian of the system. The electron would have some maybe kinetic energy, maybe it is in an external potential of some kind, so there is a Hamiltonian, but when you add and you switch on a magnetic field there is an extra contribution which is the magnetic Hamiltonian if you like. So let me call this H magnetic, which is equal to minus mu dot B, the magnetic dipole moment dotted with B. That, as you know, is the potential energy of a magnetic dipole moment in an applied magnetic field B. And if you put this in, this becomes equal to mu B, which is a number, and then sigma dot B. That is the Hamiltonian. Okay. And now if you start with the system in some state, you could change this state by switching on this Hamiltonian and then letting the system evolve as time goes along, and you will have to see what happens. Now what do you expect classically? Classically I expect that if I have a magnetic dipole moment placed in an external magnetic field pointing this direction, then this dipole moment precesses around. The component of the magnetic moment along the field does not change in magnitude, and the other two components conduct simple harmonic motion, undergo simple harmonic motion. So you have a precessional motion, and the tip of this magnetic moment vector traces a circle and forms a half cone about the direction of the magnetic field, and the precession frequency is easily computed. It is the Larmor frequency of precession, which is trivially computed once you write down the equation of motion for the dipole moment. And what is that classically? So classically the rate of change of the, so this is completely classical, this mu is different from all these other mu's I have talked about. If you have a magnetic moment dipole moment mu, then d mu over dt is equal to the torque on this guy. And what is the torque? The torque is mu cross B, and there is a constant. Why did I write a mu here? Actually it is an angular momentum, because mu is proportional to the angular momentum. The rate of change of angular momentum is equal to the torque. So since the magnetic moment and the angular momentum are connected through some gyromagnetic ratio, it is essentially d mu over dt times some constant. So there is some constant sitting here and then a mu cross B. The moment you have an equation of motion of this kind, you know immediately that if this is the direction of B and that is the initial direction of mu, then all that this does is to trace a path of this kind. The tip of this vector traces a cone, because the direction along the component of mu along the magnetic field does not change, and that is easily found because all you got to do is to dot both sides with mu with B. The magnitude of this does not change either, because all you have to do is to dot both sides with mu. So the magnitude does not change and this component does not change, so the only thing it can do is to move around in a circle, precess around. Okay. And the precession frequency is determined by this constant here, which will involve the gyromagnetic ratio and so on and so forth. Okay. Quantum mechanically, what do you think will happen? Well, by Ehrenfest's theorem, which I have mentioned on occasion, I expect that the expectation value of the magnetic moment would obey a classical equation of this kind. So with expectation values put around this mu, I still expect the same sort of equation here. But what does the system actually do? That depends on what this Hamiltonian is, what the direction of this magnetic field is, etc. And we really should write down now the state of the system at any given time. So let us try to compute it and see what happens. But before I do that, let me also point out that if the field is sufficiently non-uniform, then you know that a magnetic dipole moment not only undergoes a torque but also a force. So it is possible, if the field is sufficiently non-uniform and strong enough, to actually separate out different magnetic moment states, and this was what was done in the Stern-Gerlach experiment, which was the first classic, it is an absolutely classic experiment which I will describe a little later, because it is at the root of all that is being said today about quantum computing and quantum information and so on. So you very often see in books on quantum computation, you would see an SG apparatus, it means a Stern-Gerlach apparatus, in different directions you have magnetic fields and so on, We will come back to that, we will keep that at the back of our mind, but right now we will take this B to be a constant magnetic field and ask what happens to an arbitrary state of the system. You start with an arbitrary spin state of this electron, what will happen as a function of time? Well, the first thing to note is that since these two states, the up and the down, actually form a basis in this space, it is clear that any spin state of the system, and let me just denote it by psi of t, can actually be written uniquely as a superposition of these two basis states. So this can always be written as A of t up plus B of t down, where A and B are two coefficients which will depend on time in general if the psi of depends on time. Okay. And if you normalize this state, since these guys are already normalized, we are going to assume that A of t whole squared plus B of t whole squared is 1 for all time. Okay. So we will talk about normalized states of the system. Now let us do the simplest problem, and that is I prepare this system in the up state. So I tell you to start with that psi of 0 is just up, that means A of 0 is unity and B of 0 is 0 to start with, and then I switch on this Hamiltonian. Now if the Hamiltonian is in the z direction, if the magnetic field is in the z direction too, then nothing is going to happen, because if B is B times Ez, for example, then the H magnetic, the Hamiltonian, becomes mu and then sigma 3 B, sigma dot B is just sigma 3 B. Okay. This guy is an eigenstate of sigma 3 with eigenvalue plus half H cross or plus 1, because it is sigma 3 alone. So nothing is going to happen, and psi of t is e to the minus I H t over H cross. This is equal to e to the minus I mu b. Oh, I am going to find this mu sub b very inconvenient to write, I b mu b over H cross sigma 3 t, acting on this state. So what happens? It is just a phase factor here, this factor here is just a phase factor, because sigma 3 is it's a diagonal matrix, so you can compute what this quantity is, and it remains something which is proportional to the unit matrix and sigma 3. So what happens finally? What is this equal to? This is an eigenstate of sigma 3 with eigenvalue plus 1. So you can replace this sigma 3 by 1 out there. So this is equal to e to the minus I b mu b by H cross t on 1 on up. So nothing happens, it is just a phase factor. So if it starts in this initial eigenstate and you switch on the Hamiltonian, you are already in an eigenstate of the Hamiltonian and it just remains there apart from a phase factor, e to the I e t over H cross. Does not do anything interesting. Similarly, if I started with down and I applied a field in the z direction, nothing is going to happen. But if I start with an arbitrary state, a superposition of up and down, this is a superposition of up and down, then of course interesting things are going to happen, because a part of it, whenever that Hamiltonian acts on this state, you are going to get plus there, and when it acts on this state you are going to get minus 1, and you will have a superposition of two exponentials, there could be interference and so on. So this is already telling us how in the simplest of instances quantum interference would play a role. Now classically, if you got a dipole lined up like this and you want to make it lined like this, or you want to change its alignment, what would you do? There is no use applying a field in this direction. you have to apply a field in the transverse direction, or at least have a component in the transverse direction. So let us do that. Let us start with the dipole in the electron in the up state, and let us apply a transverse field in the x direction. Now let us see what happens. So this H is mu b, so the b I am going to apply is b times Ex in the x direction. So this is mu b times b sigma 1, it is the x direction, so the first Pauli matrix comes in. And then what does this guy do? Psi of t equal to e to the minus, let me put these factors in so that minus I over h cross, we will do that once, b t, so let me put those factors in, and then mu b was modulus E, I want to put these factors in, h cross over twice the mass, and then a sigma 1, and this acts on this state there, the initial state. So the h cross cancels out, which will be this will be relevant, you will see what the significance of that is, and that is equal to e to the minus I mod E over 2m EB over 2m times sigma 1 acting on this guy here. What is EB over m? If you have a charge E of magnitude E in a magnetic field of magnitude B and the mass of this charge is m, what is this combination EB over m? It is the cyclotron frequency, right. So this is equal to e to the minus I omega cyclotron t over 2, and then there is a sigma 1 and it acts on this fashion. Now this is not a pure phase factor by any means, because there is a sigma 1 here, and that is not an eigenstate of sigma 1, this is an eigenstate of sigma 3. So you really have to write down what this quantity is explicitly, let us see. So let us work it out just this once. So psi of t is equal to, now this is the form, let's use this general formula which we already wrote down, e to the power I a dot sigma, where a is an ordinary vector, a C number vector, this is equal to e to the minus I is what I want, minus is equal to cos a times the unit vector minus I a dot sigma over a, but it is the magnitude of this vector, sine a. That was the generalization of this Euler formula, e to the I theta is cos theta plus I sine theta. How do we get this formula? Well, you use the fact that the square of each sigma matrix is 1 plus the commutation properties of the various sigma matrices. I think I gave this exercise in one of the exercises in linear vector spaces. So let us use this formula explicitly. In our present instance, A is equal to omega c t over 2, a unit vector in the x direction, because we got a sigma 1 here, a dot sigma was this guy here. So psi of t is equal to cos omega c t over 2 I minus I a dot sigma is this a cancels, sigma 1 sine omega c t. This whole thing acting on this guy there, okay, and that is explicit now. So this is what it is exactly at any later instant of time. Well, let us compute what it is, let us work it out. So psi of t equal to, it is a ket vector of some kind which is going to be written as a column matrix, and this is equal to cos omega say t cos omega c t over 2 and then minus I, remember that sigma 1 is 0 1 1 0, so I am using that, minus I sine omega c t over 2 minus I 2, that is this matrix acting on 1 up, but that is 1 0, okay, and that gives you, it is this cos omega c t over 2 times 0, and then it is this and 0 and then this and 0, so minus I sine over 2, okay, which is equal to cos omega c t. We could have guessed this right away, that is the up matrix minus I sine over 2 and then that is the down state, okay. So that is my A of t and my B of t, and it is clear that mod A squared plus mod B squared is 1 at all times, it is normalized as you would expect. A of 0 is 1 as it should be, we started with the state up, and B of 0 is 0. Now what is the significance of these coefficients? Since I expanded this in the basis up and down, what is the significance of these coefficients? What is the interpretation of these coefficients, or rather the mod squareds? It is the probability I start with the electron in the spin up state, I switch on a transverse magnetic field at t equal to 0, then this gives me the probability, mod A squared of t gives me the probability that at time t the state is up, and mod B squared is the probability that the state is down. The sum of the two must always be 1. So it is immediately clear that we could write this down and plot as a function of t, I plot the probability up of t, that at time t thing is up, this is equal to mod A of t whole squared, and that is equal to cos squared omega c t over 2, okay. And what does that graph look like? It goes up and down as this. On the other hand, the other fellow starts like this and does this, and this is equal to p down time t, this is equal to sine squared over 2, okay. And the frequency with which this happens is precisely omega c, because cos squared is 1, you can write this in terms of cos twice the angle, so the periodicity is that of cos or sine omega c t. So quantum mechanically this Hamiltonian, which is in the transverse direction, plays the role of a spin flip operator. It flips the spin from up to down and down to up repeatedly, and at any time t the system is actually in a superposition of the two states, except at those special instances where either A or B vanishes. So that is what happens quantum mechanically. You can't say that the system is definitely in the up state or the down state, unlike what you could do classically. This is because the Hamiltonian does not commute, it is not the Hamiltonian is not an eigenstate. I mean, these up and down states are not eigenstates of the Hamiltonian, but we insisted on using that as our basis. Yeah. Yeah. Yes.
It's certain that it is up
yes,
or down.
at those instants of time with probability 1 it is either in the up state or in the down state, but only at those instants of time.
Isn't that a problem?
Pardon me?
Isn't that certainty a problem?
No. Why is it a problem? Why is it a problem? Why is that a problem?
You don't like to be certain about anything in quantum.
But psi of 0 is
Quantum mechanics is uncertain, but it is not uncertain in that sense, it is very deterministic. You see, quantum mechanics is a way of computing probabilities, certainly that is true, but the actual rule for computing these probabilities, expectation values and so on, those rules are quite deterministic, there is nothing arbitrary about it. What I want to illustrate by this example is the power of is the basic nature of superposition. That you start with an eigenstate and then you switch on a Hamiltonian, this is not an eigenstate, the state you start with is not an eigenstate of the Hamiltonian, and then the Hamiltonian takes you through all the other states of the system, which in this case is all the other states of the basis. There are only two in this particular instance, but it causes these flips, spin flips. So sometimes, therefore one sometimes says that a transverse magnetic field causes spin flips. This is the way to flip a quantum mechanical spin, and this is with a constant field in the z direction. I am going to leave it to you as a problem to work out what happens if I start with an arbitrary state, some A of 0 and some B of 0 normalized to unity, and a magnetic field in an arbitrary direction. It is not very much harder, the algebra gets a little more complicated, but you can see easily that in this 2-dimensional space you always have a superposition of the up state and the down state, that is it. Suppose I have an eigenstate of sigma x of sigma 1, right. I could sort of pictorially write it like this or something, show that in the x direction the eigenvalue is. This can also be written as a superposition of up and down. Any state, any spin state in this Hilbert space can be written as a superposition of an up and a down. Okay, that is important to remember. Okay. Now all this was with a constant time independent Hamiltonian. If I start now switching the Hamiltonian on and off, switching a field on and off as a function of time, matters will get considerably more complicated. Then we need a new formalism, we need to know what to do when you have a time dependent Hamiltonian, because e to the power minus IHT over h cross is no longer the time development operator. We have to be a little careful, we will do that too. Okay. So is this clear? Yeah. Pardon me? Well, okay. Now the fact that you have, let me say that quickly and then we come back and talk about it in greater detail. What we have at hand is a 2-level system in some sense. There are just 2 states possible, and an up and a down. So if you assign energies, remember that we wrote H is equal to mu b sigma dot b here, and if I now say that the magnetic field is along the z direction, for example, then this Hamiltonian becomes this guy becomes mu b times sigma 3, and this has eigenvalues plus minus 1. So the energy levels of this system, the eigenvalues of this would correspond to, for down state it is this, and for the up state it is that, and there is a gap between them. This energy minus b mu b and this energy is plus B mu B, and there is a gap of 2B mu. This corresponds to a 2 level system, but it is not an ordinary 2 level, it is a quantum mechanical 2 level system. Therefore, any superposition of these two states is a general state that you have, and this superposition gives you enormous freedom because you have two coefficients A and B such that mod A squared plus mod B squared is equal to 1, and therefore you really have an infinite number of superpositions possible. So in some sense the fact that you start with a 2 level system but really you have an infinite number of possibilities, that is what leads, this is why it is called a qubit as opposed to a classical bit which would be a 0 or a 1, but you are starting with a 0 and a 1 if you like. I mean you are starting with a down state and an up state, but all possible superpositions are allowed. Therefore things are a little more complicated. It is the superposition that is going to lead to all the interesting features we will talk about a little bit. So this tells you what happens in the simplest 2 level system when I switch on a transverse magnetic field. Okay. Let me also introduce another concept here, then we will come back to this, and this is the concept of entanglement, which is something which is very, very common these days. Let me mention what this means. Suppose you have two 2 level systems, two of them, 2 electrons, and I look at the spin states of the 2 electrons together. I am not interested in the other degrees of freedom, I am not interested in the Coulomb interaction, I am not interested in their potential energy due to the Coulomb interaction, I am not interested in the kinetic energy due to their motion and so on. I am looking only at the spin states of the system. Then what does the Hilbert space look like? For the first electron you have a Hilbert space H1 and it has 2 states which would correspond to either up or down for the first electron, that is this Hilbert space. For the second one similarly I have an up 2 and a down 2, I have these 2 guys. Okay. Now I put these 2 together and I look at the states, possible states of the full system. How many states would you say there are? Yes, there are 4 possible states to start with. You would say naive guess would be say up up or up down or down up and down down. You would say there are these 4 states, but now the matter gets a little more complicated. We need to know how to add angular momenta in quantum mechanics. We are going to do this, but let me state the result which you have already learnt in spectroscopy. If you have 2 angular momenta J1 and J2, the quantum mechanical rule for adding these angular momenta, and J1 and J2 are independent of each other, the components of J1 commute with the components of J2, no problem, but among themselves the components of J1 satisfy the angular momentum algebra, and similarly for J2. Then the question is, if I add these 2 and I call this the total angular momentum here, what are the possible values of this capital J or J squared? What are the eigenvalues of J squared given the eigenvalues of J1 squared and J2 squared? This is the theory of the addition of angular momenta, and I will make a short excursion to that a little later. But you already know the answer, and the answer is that if this thing here J squared has eigenvalues J times J plus 1 H cross squared, and this has spin as quantum number J1, so it is J1 into J1 plus 1 H cross squared, and this is J2 into J2 plus 1 H cross squared, then the rule of addition of angular momenta tells you that little j can take on a large number of possible values ranging from modulus J1 minus J2 up to J1 plus J2. Okay. Are you familiar with this rule in spectroscopy? Yes? No? Never heard of it? And so on. We will establish this. This is a very well known rule in addition of angular momenta. I thought they taught this in 6th grade or something like that nowadays. I am pretty sure it is there somewhere in the textbook, because some wise person must have decided that 6th standard children can't survive possibly in life without knowing this rule. But this rule of addition of angular momenta, I have seen this, by the way, I have seen it in school textbooks. It's, from here to here. Okay. Don't ask me why they say that, but it's true. Okay. It's not very hard to derive, we will do this. But you see already that quantum mechanical angular momenta are not going to add up like classical vectors. Not surprising, because these are operators, they are vector valued operators. So this is an operator and that is an operator, and therefore they have their own peculiarities, and this quantum number can take on all values from here to there. Any component adds up linearly. For example, if this J1, the Z component of it, let me put a superscript there to show the Z component, if this is equal to M1 H cross, because it must have eigenvalues which are some multiple of H cross times this quantum number M, magnetic quantum number M1, and this M1 can run from minus J1 to plus J1 in steps of unity. Similarly, J2Z is M2 H cross, then Jz is M1 plus M2 H cross. They add up completely linearly, because these two fellows commute with each other, there is no difficulty, and if you are in an eigenstate of J1Z and J2Z with these eigenvalues, then you are also in an eigenstate of capital Jz with this eigenvalue. Okay. But the allowed values for the total quantum number run from here up to there. Okay. Take this as a given rule for the moment. Okay. Then the question is, what happens if I add the spins of 2 electrons? Each of them is a 2-level system if you like, and what if I add the spins of the 2 electrons? What are the possible eigenvalues of S1 plus S2? This is the total spin operator. What's the total, what are the possible values of the total spin quantum number S? Let us use this rule. What's J1 in this case? It is just S1, and what's that? Spin half, no H cross, it is just the quantum number, it is half. This quantum number is half for the electron, the spin quantum number is half, it can't be negative, it is a number 0, half, 1, etc. And I already said the electron spin quantum number is half. That is so for every electron. So it is completely clear that in this case this is a half and that is a half. So this total spin quantum number can be equal to 0 or half plus half, which is 1. So you see you have 2 quantities, 2 components, 2 objects, each of which has spin quantum number half, angular momentum quantum number half, but they can add up to 0, and they can also add up to 1. Pardon me? They clearly cannot add up to half, they can't add up to half, because it runs from here to there in steps of unity, and it cannot add up to half. But I also said that something with a half odd integer quantum number is a fermion, and something with an integer quantum number is a boson. I will explain what these things mean, they have to do with statistics. So it implies that you take 2 fermions and you put them together, you can create a boson. This has profound implications, very deep implications. This is how superconductivity occurs, okay, for instance. So there are many implications to this, but the fact right now I want to emphasize that the total spin quantum number can be either 0 or 1. Then the next question is, what are the possible states? What are these actual states? What do they look like? We have these 4 states here, and now the actual space is the direct sum of this space and this space. The states that we are talking about are 4 in number. They could be either 1, direct product, 2, and so on. There are 4 of these direct product states, and I would like some slightly less complicated notation for this. So let me do exactly as I did when I took 2 simple harmonic oscillators and constructed the angular momentum algebra, exactly the same way. Let me just write this as up, up, with the understanding that the first arrow always talks about the state of the first electron, and the second arrow will the state of the second electron. So I have 4 of these states, up, 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 down, down, up, down, down. They obviously form a basis in the full Hilbert space. So every state, spin state of both the electrons can be written as a superposition of these 4 states. Now the question is, what are these states? What do they correspond to? You see, the moment I say S equal to 0, then it also implies that Sz is equal to 0. So if these are eigenvalues that I am writing down here on the right hand side, because if this is 0 in units of h cross always, this must be 0, because a single component cannot have a non-zero value while the total quantum number is 0. The square of this angular momentum has eigenvalue 0, so every component definitely has eigenvalue 0 also, even if they do not commute with each other. That is a state of 0 total angular momentum, is a state in which every component of the angular momentum has eigenvalue 0. So here is an example where 2 operators which do not commute with each other can have a common eigenstate, the trivial case of 0 total angular momentum. Then every component of the angular momentum also has 0 as the eigenvalue. This is the only possibility here. But the moment I say S is 1 in units of h cross, then what are the possible values of Sz? So corresponding to this you have this, and corresponding to this, what are the possible values? Remember, it can go from minus the total quantum number to plus the total quantum number in steps of 1, minus little j to plus little j in steps of unity, and now this S is 1. So what are the possible values? Can be minus 1, 0, plus 1. So you have 3 possible states here, substates here if you like, or states in this space corresponding to S equal to 1, and in this space you have a 0 here. There are 4 possible states. They must be linear combinations of these 4 possible states, linear combinations, and it is these states that we would like to describe in terms of those direct product states or the basis set. So what would they be? How would you write this down? And now let us write these states down as the total S and Sz. This is my J, remember, recall the Jm notation. That is exactly the notation I am going to use. So I would like to write 0 0 equal to, that is this state, zero 0, what is that equal to is the question. Can it be this? Because remember, this corresponds, remember, in any component the angular momenta just add up. So this corresponds to S1z equal to plus half h cross, S2z is plus half h cross. So Sz must be equal to H cross. So that fellow actually corresponds to this. Similarly this fellow corresponds to this because both are down and those are easily written down. So 1 1 can be written down and that is just up up. 1 minus 1 can also be written down, and let me leave a gap and write it. 1 minus 1 can be written down and that is down down. Okay. What we are left with is to answer what is 1 0 and what is 0 0. We need to know these two. Which is which? This also has Sz equal to 0 because one is up, one is down. So does this. This is down, that is up. How will you choose? How will you say this corresponds to that or this corresponds to this or any superposition of the two? How would you decide? You decide by what is called the symmetry property of the states. This thing here is called a singlet state. S equal to 0 is called a singlet state. The reason is there is only one state, there is only one Sz possible. On the other hand, S equal to 1 has 3 possible states associated with it. And therefore what would you call this? The triplet state. This is called the triplet state. So this is the singlet and these 3 fellows together form the triplet. Now you notice that the singlet state sits alone out here and the triplet state is one set, sits alone here, and this triplet state, this state here and this state here have a certain symmetry property. Suppose I exchange the 2 electrons, I interchange all the degrees of freedom of this electron with that, exchange these 2 electrons. Does this state change at all? Does this change? It does not change at all. It is symmetric under the exchange of the 2 electrons, it is completely symmetric. Since the 2 electrons, remember, are indistinguishable from each other. So really under the exchange of these 2 electrons this state has remained exactly the same, it is indistinguishable. And so is this. Now it turns out that all the members of a multiplet must have exactly the same symmetry properties. This is the whole idea of putting them together in one bin. Therefore this state must have total Sz equal to 0, that means if one arrow is up the other arrow must be down, but in such a way that when you exchange the two the state does not change at all. What would you do? You have this and this as the 2 possibilities, but if I exchange the 2 I go from here to here and this goes from here to there. So what should I do there? Superpose the 2. So this is up down plus down up divided by square root of 2 because I have to normalize this. Each of these is normalized to unity and therefore if I divide by square root of 2 I normalize this state. And then of course the other state is an orthogonal superposition, and what would this be? It must be orthogonal. Every state here must be orthogonal to all the states. So what is this got to be? Minus. Now you could ask, why did I choose up down minus down up? Why didn't I choose down up minus up down? It just multiplies it by a phase factor, it does not do anything to it. Multiplying this by any complex number of unit modulus does not do anything to the state, it is exactly the same state. So this is antisymmetric under the exchange antisymmetric and this guy is symmetric. This is the spin part of the state, but you know there is something called the Pauli exclusion principle for these particles, which says that if you have two electrons, they are absolutely identical, then in no matter what state these electrons are in, the total state must be antisymmetric under the exchange of the two electrons. But this is only the spin part of the wave function. There is also a spatial part. If these fellows are moving about, then in the position representation there is a psi of r1 r2 and t, a wave function, and product of that with the spin wave function is a total wave function, and that must be antisymmetric. So this immediately says that when the two electrons are in the singlet state, the spatial part of the wave function must be symmetric under the exchange, so that this antisymmetry gives you an overall minus sign, and in the triplet state the spatial part must be antisymmetric and the spin part is symmetric. This plays a fundamental role in all of physics. This idea that when you have these two electrons and the Pauli exclusion principle is implemented in this fashion. So what you have to remember is that the spin singlet state is antisymmetric and the spin triplet state is symmetric. And notice that we got these linear combinations by imposing that all the members of this multiplet have the same symmetry. That is why they are part of the same multiplet here. Now the question is, what do I mean by entanglement? The answer is these states, this state and this state, cannot be written as a direct product state. These are direct product states, but a superposition of these states. So the fate of one electron is inextricably linked with that of the other electron in these states. This is called entanglement, and it has very deep consequences. Yeah.
Sir, can we have the
No, because triplet state must have this. This is symmetric automatically, and this, that is symmetric, and we have no choice after that. We have absolutely no choice. I will subsequently show how this also leads to the phenomenon of magnetism, because this very simple observation is actually going to lead us to a so called exchange interaction. This was Heisenberg's discovery. It explained the origin of ferromagnetism. So we will talk about that, but right now I brought this up in order to tell you what entanglement is, but we are going to come back to this concept and talk. Yeah. Pardon me?
Is the beginning of these three states,
Yes.
is that a postulate or?
No, the fact is that what you mean by, no, it is not a postulate, you can derive this thing. You could derive this from the rules of addition of angular momenta, but what I gave you was a very compelling reason, namely when you put systems together in a certain, this is an irreducible representation. How should I say this? The three components of an ordinary vector are not three random numbers or anything like that. They go into each other under rotations. In an arbitrary rotation, a given vector becomes a linear combination of the three components here, right? So together those three quantities transform in a specific manner under rotations. In exactly the same way, the fact that these three members are all symmetric under the exchange is part and parcel of there being a multiplet. This is essential, it is necessary to do this. But I want you to appreciate that these are not writable, these states are not writable as direct product states. That is the crucial point. Although this one happens to be and this one happens to be so writable, the other states are not so writable. Okay. So we will come back to these concepts a little bit and talk about what happens. Okay. Let me do that tomorrow.